so which may hinder the flow of electron to this part. So the sodium Na plus ion from this salt bridge gets intact with this nitrate ion and make it neutralized. So which and in turn in the left side what happened, there is formation of zinc to zinc 2 plus because oxidation is happen here. So this zinc 2 plus, the number of zinc 2 plus in the left hand side will become more and more. So to maintain the neutrality, this nitrate ion will react with the zinc 2 plus ion to make the zinc nitrate again. So by this method, what happened that this salt bridge maintain the neutrality, and gradually we see that this copper plate becomes thicker and thicker, and this zinc plate becomes thinner and thinner. Okay, so by connecting these two parts with one voltmeter, we will have the potential difference of 1.1 volt. And here as electrons are evolved or generated from zinc, so it is the anode, and as electron gets accepted or gained by the right hand part of this cell, this is known as the cathode. Okay, just remember, cations, that is cu2 plus, cations are accepted or attracted by the cathode, and anions accepted or attracted by the anode. Okay, that means this will be your notation, that is a zinc anode and copper cathode. In anode oxidation takes place, in cathode reduction takes place. Okay, so the movement of electron will be from zinc to copper, and movement of cation will be from zinc to copper, and movement of anion will be from copper to zinc. That is there, this is indicated here. This is a movement of cation and this is a movement of anion. That means zinc gets oxidized and copper gets reduced. Okay, so just remember one thing, oxidation is happening at the left hand side of this cell, that is anodic cell, and reduction is happen at the cathodic end. Okay, so to remember these things very easily, and do not confuse with these notations, that is where which is anode, which is cathode, which is negative, which is positive. Just remember one one line here, just I write here, that part is LOAN, loan. Okay, so what is loan? In electrochemical cell or voltaic cell or galvanic cell, this this loan concept is helpful to us to remember or to have no confusion, which one is anode, which one is cathode, which one is negative, which one is positive, what will be the notation, what will be the reaction. Just remember this small word, that is loan, LOAN. So L stands for left hand side. So just see, the left hand side is this one, that is zinc. It is the left hand side. O stands for, it is oxidation. So at left hand side, oxidation is happen. A stands for anode. That means the left hand side is anode. And N stands for, it is negative. Just see here, the negative part is here. That means in a electrochemical cell, voltaic cell, or galvanic cell, or battery, the simple rule is LOAN, loan. That is the left part having the oxidation reaction. This is the anodic part, and the notation is your negative. So what will be the right hand side? It is R. Oxidation means it is reduction. Anode means it is cathode. Negative means it is positive. But just see, these things are here. The right hand side, reduction is happening, it is cathode and it will be positive. So just try to remember this small word that is lone here, and accordingly you will remember and understand the things. Then we have okay, this is again the voltaic cell, the same thing, that is the concept of your galvanic cell or battery, in which electrical energy is produced uh, by the chemical reaction. Here it is written, that is a salt bridge concept, it is U-shaped, and the cations are moved towards cathode, anions are moved towards anode. Just remember these things. Cation towards cathode, anion towards, that means cation is positive, cathode is negative, anion is negative, anode is positive. Okay, so try to remember these things. In the cell, electron leaves the anode and flow through the wire to the cathode. It is already understood that electron is released from the zinc anode and it is accepted by the copper cathode. As the electron leaves the anode, the cation formed dissolve into the solution in the compartment. Then the anode will decrease in size. Okay, so gradually this zinc becomes thinner and thinner, and copper gets thicker and thicker. As the electron reaches the cathode, cation in the cathode compartment are attracted to the now negative cathode. The cathode will increase in size. That means cathode gets thicker and thicker, and the zinc gets thinner and thinner. The same thing. The metal is deposited on the cathode. That means copper is deposited on this copper plate. Yes, this is the thing for which lots of mechanisms, lots of exercises are going on. That is the potential. Just you remember, if you if you if you buy a battery, a small battery for your wall clock, then that battery is written 1.5 volt. If you buy a large battery, bigger size battery for your torch, it will be highlighted with 6 volt. This volt is the unit of your potential, and this potential is generated through a complete cell. That is when the left cell and the right cell, or the oxidation half cell and the reduction half cell gets connected, we will have a difference in potential, that is known as the cell potential. So before going through the cell potential, we will have a look on your electrode potential. What is electrode potential? That means here just see, here a zinc is an electrode, this is zinc electrode and this is copper electrode. So here what happen, zinc gets oxidized and copper gets reduced. Okay, that means it is the potential of this electrode, zinc electrode, to get oxidized. So this is known as the oxidation potential, and this will be the electrode potential of the zinc. And it is the potential of the copper electrode, it is the potential of the copper electrode to get reduced. So this is the reduction potential, which is responsible to get the copper in the reduced form. So that means copper 2 plus 2 copper. So this type of potential, that is whether one ion or element gets oxidized, or one ion or element gets reduced, it depends on its potential. It is just a potential of the itself, that whether it gets oxidized or reduced. So so by combination of both oxidation potential and reduction potential, we will have the net potential of the cell, which is known as cell potential. Okay, so here what happened, the standard reduction potential, Standard reduction potential means what? It is a reduction potential at standard state. What is standard state? Standard state is where the electrolyte concentration is maintained at 1 molar concentration and at 1 atmospheric pressure. This is or and at your temperature, that is 298 Kelvin, 25 degrees centigrade. So this is the standard condition. So at this condition, when the potential is determined of a particular element or a cell, it is known as standard reduction potential. Okay, and always you should remember the potential of any element is determined when this is coupled with the standard hydrogen electrode. So what is standard hydrogen electrode? It is, in short, it is known as SHE. SHE, that means standard hydrogen electrode. The standard reduction potential of standard hydrogen electrode is 0 volt, because these hydrogen electrode do not produce any electricity, and we will go through that one. Just I will highlighted some of the basic things you should know before going through the depth of this chapter. Just you should know that the electrode potential of any element is determined by coupling it with standard hydrogen electrode, and the standard reduction potential of standard hydrogen electrode is 0 volt. That means if I want to determine the electrode potential of zinc, what I will do? I will do this zinc electrode is coupled with the standard hydrogen electrode. Here no copper is there, it is standard hydrogen electrode will be there, and the same thing, one voltmeter is attached here. Then by with the chemical reaction, what happen? This voltmeter will show minus 0.76 volt. That means for hydrogen, the potential is 0 volt, and the voltmeter show minus 0.76 volt. So where this potential difference will arise or come? It is coming because of this zinc electrode. So it is concluded that this electrode potential of zinc is minus 0.76. At the same time, if I wish to determine the electrode potential of copper, what will I do? I will couple this copper electrode with standard hydrogen electrode. Here this is the standard hydrogen electrode becomes. So these two will get connected and chemical reaction will happen, and this voltmeter will show plus 0.34 volt. That means for hydrogen it is 0. So where this 0.34 volt come? It is due to the potential difference between hydrogen and copper, and this is due to, that is 0.34 volt. It is due to only copper. So by this method, the standard reduction potential of different elements or compounds, because not compound, only elements or ions are determined by coupling with standard hydrogen electron. So what is cell potential? It is the potential difference between anode and cathode. That is the oxidation half cell anode and the reduction half cell cathode. It is a difference in potential. That means if I say zinc and copper, so where zinc gets oxidized and copper gets reduced. So this is the cell potential will be the potential difference between zinc and copper. So it is a measure of driving force, and this cell potential, it is symbolized as E cell, and this is also known as electromotive force, EMF. This cell potential is also known as EMF, that is electromotive force. Okay, so 1 volt, that is a cell potential, it is equal to J by C, that is joule per coulomb. Then yes, this is a standard reduction potential. Just see students, here what happened, fluorine is at the top, and before going through this table, I would like to say some lines that according to the recent rule framed by IUPAC, International Union for Pure and Applied Chemistry, IUPAC, International Union for Pure and Applied Chemistry, we will measure the cell potential, or we will have any mechanism or anything related to electrochemistry, related to cell potential or electrode potential, everything should be measured in terms of reduction potential. This is not in terms of oxidation potential, it is a reduction potential. And if the reduction potential is measured at standard state, that is at 1 molar concentration, 298 Kelvin, and 1 atmospheric pressure, at that condition, the reduction potential is said to be standard reduction potential. Here just see, there are various ions are here, and you just see here, you just see here, the first element is fluorine. So fluorine has the highest reduction potential. So what is reduction potential? This is the potential of an electrode to gain electron. If fluorine has the highest power to gain electron, that means it will snatch electron from any electrode or metal or atom to which it is coupled. That means fluorine has the highest potential or ability or the power to accept or gain electron to get reduced. That means here F20 gets 2F minus 1. 0 to minus 1 means it is reduction. Similarly, in this table, lithium, the last element, it has the lowest ability or least ability to accept electron. Okay, and it has the ability of minus 3.05. So, so from where these values are taken? These values are taken, or these values are determined when these ions or elements gets coupled with standard hydrogen electrode, for which the electrode potential is always zero, the standard reduction potential. Just see here, sorry, yes, just see here, this is the hydrogen, 2H plus 2 electron minus, this become means it is reduced to give hydrogen gas. So for this reaction, the electrode potential is 0 volt. That means if this hydrogen electrode is coupled or connected with any of the metal or any of the ion or any of these atom or ion, what happen? There will be, there will be change in or difference in potential, which is highlighted through the voltameter. If I coupled hydrogen electrode with, let us, fluorine, the voltameter will show plus 2.87. That means for hydrogen it is 0, so voltameter will show 2.87. So that means 2.87 is for fluorine. If I connect this hydrogen electrode to aluminum, the voltameter will show minus 1.66. So this is for aluminum ion. So by this method, the different cell potential, so different electrode potential in terms of standard reduction potential is arranged uh, by a table in a descending order, and this table is known as electrochemical series. Sorry, um, yes, electrochemical series, that is ECS, electrochemical series. And just remember here, fluorine is the most oxidizing agent, and lithium is the most reducing agent. Okay, so here it is written, the species with the more positive value of potential will be reduced. That means more is the value of the positivity, the elements get the element easily reduced, and the species below this table will have the most oxidized, or will be oxidized easily. That means this positive part will be reduced easily, and at the bottom or at the below part of this table, this element will be oxidized easily. Then standard cell potential, it is already told to you that cell potential at standard condition, 1 molar concentration, the cell potential, uh, standard cell potential is denoted as E0 of all galvanic cell of positive value and happens spontaneously. The oxidation half reaction will be reversed from how it appears on the table, and the value of its voltage will have a reverse sign too. Okay, so just see this table. If I say fluorine has the reduction potential of plus 2.87, I also I can also say fluorine has the oxidation potential of minus 2.87. That means if I change the sign plus to minus or minus to plus, the reaction is also gets reversed. That means fluorine reduction potential is plus 2.87. Fluorine standard oxidation potential will be minus 2.87. Similarly, for lithium, the reduction potential is minus 3.05. What will be the oxidation potential? It is plus 3.05. Okay. So by changing the positive and negative sign, we can designate the respective reduction potential as well as oxidation potential. Just see the same thing here, zinc and copper. This is just a galvanic cell or voltaic cell of zinc and copper. So just from this table, just see copper has the potential of 0.34 volt here, and zinc has the potential of minus 0.76. So from these two values, we we conclude that between plus 0.34 and minus 0.76, plus 0.34 is a larger value than minus 0.76. That means with the element or the ion which have the larger value of standard reduction potential will get reduced, and the other ion will be oxidized. So what will be the reaction? The reaction with, this is the oxidation part, this is the reduction part. It is the values written here. It is wrongly written. This is minus 0.76. Okay. So it is here electropotential of anode. This is plus 0, this is minus 0.76. Of cathode it is plus 0.34, and we will have, here it is written plus 0.76. That means the reduction potential is plus 0.376, but the oxidation potential will be, sorry, the reduction potential is minus 0.76, then the oxidation potential will be plus 0.76. We have to just add these two potentials, the oxidation potential of the oxidation half cell and reduction potential of the reduction half cell. So this is the reduction potential 0.34, and this is the oxidation potential of zinc, that is 0.76 plus. So if we sum of these two, we will have a plus 1.1 volt, that is highlighted or indicated through this voltmeter. Okay, so do not confuse. This is written as electrode potential of anode. That means it is the oxidation potential. So if zinc has the reduction potential of minus 0.76, what will be the oxidation potential? It will be plus 0.76. And from that table, the copper is the cathode. The copper has the reduction potential of plus 0.34. So by sum of these two, we will have the net or net potential of the cell, that is 1.1 volt. This is the cell notation. How to mm, uh, how to abbreviate, or how to get the symbol of a cell. What will be the writing? What will be the method of writing? Just remember, at the left hand side we will have the oxidation half cell, that is the anode. What is our anode? It is zinc electrode dipped in zinc sulfate solution. What is zinc sulfate solution? It contains zinc ion. zinc 2 plus. Aqueous means it is at the in the aqueous medium. Then double line. Double line means it is the salt bridge, that is sodium nitrate in agar agar medium. Then the cathodic part, right hand side part, that is copper 2 plus. This is just the opposite writing. Here copper electrode, that is copper solid, is dipped in copper 2 plus. They are just see, this is zinc 0 to zinc 2 plus, that means oxidation. This is copper 2 plus to copper 0, that means it is reduction. So this is the way we should write a cell, that is the oxidation should be from lower oxidation state to higher oxidation state, followed by the reduction from higher oxidation state to lower oxidation state, with these two will be separated by a salt bridge. Just here it is written, this is the anode electrode, this is the anode electrolyte, and here the electrolyte is first, followed by the electrode. This is the cells which we generally buy from market, Duracell. Then we have Nippo and Eveready batteries are there. So these are the simple voltaic or galvanic cells. A metal air electrochemical cell is a portable electrochemical cell that uses the anode made of a pure metal and external porous cathode that lets in the oxygen. Just these are very simple things. Okay. This is the electrolytic cell. So an electrolytic cell is the reverse of electrochemical cell. That means the mechanism happening in galvanic or voltaic or electrochemical or battery, it gets reversed in electrolytic cell, where the electrical energy is converted to chemical energy. So how this situation came that one cell gets reversed. The situation is when uh, zinc gets converted to zinc 2 plus. Just see these things. When zinc gets converted to zinc 2 plus and copper 2 plus gets converted to copper solid, then by going through this reaction, a point will reach where the zinc 2 plus ion and copper 2 plus ion concentration becomes equal, and they will be in equilibrium, and the voltmeter will show zero reading, 0 volt. At that time, we can say, at that time we can say that an equilibrium is reached between zinc electrode and copper electrode. Okay, so to um, so at this situation, we will we can apply external electricity to that cell in reverse or in opposite direction. The what is the opposite direction? That means this anode gets positive and this cathode gets negative. Electrolytic cell, the anode symbol becomes positive and the cathode becomes negative, and there will be reverse flow of electron. If reverse flow of electron will be there, that means the reaction will again start. That is, copper plate which is become thicker and thicker gradually becomes thinner and thinner, and the transparent solution of this copper will becomes bluish. And similarly, the plate which is becomes thinner and thinner due to oxidation gets reappeared or becomes thicker and thicker due to the reverse flow of electron. This is the concept of your electrolytic cell. Just see here, it is the external power is supplied here, and anode is positive is now, cathode is negative. So this situation arises when equilibrium is established, that maximum copper gets copper 2 plus gets converted to copper, and zinc 2 plus zinc converted to zinc 2 plus. So at that time what happened, the external supply of electricity is needed, and by the external electricity is supplied in opposite direction. That means the anode becomes positive and cathode becomes negative. That means electron gets the electron are generated from the copper end and will be gained by the gained at the zinc end. That will the electrolytic cell. So an electrolytic cell, this external battery is connected, this anode becomes positive and cathode becomes negative, and there will be opposite movement of electron. An electrolytic cell is an electrochemical cell that drives a non-spontaneous redox reaction. This become non-spontaneous because as equilibrium is reached, the reaction each seems to be stopped. There will be no reaction. There will no flow of electron will be happening because the equilibrium is reached. And to continue the reaction or to make it spontaneous, we have to supply some external electric energy. So they are often used in decomposed chemical compounds. Yes, the chemical compounds which gets generated should be decomposed. That is, copper gets deposited on the copper plate, and zinc plate becomes thinner and thinner. So gradually what happens, the reverse reaction will occur. That means copper solid will change to copper 2 plus and the electrolyte becomes blue, deep blue. And at the same time the zinc 2 plus will converted to zinc by the gain of 2 electrons. This is the next part, that is electrolysis of water. So electrolysis of water, we have two things, that is cathode and anode here. So at the cathodic end, what happened? The H plus ion from the water is added by 4 electrons to give H2 gas, and at the same time at the anodic end, the oxygen O2 minus will gain 4 electron to give oxygen gas. This will be the net reaction, that is 2O2 minus plus 4H plus 2H2 plus O2 gas. So electrolysis of water is the decomposition of water into oxygen hydrogen gas by passing of electricity. The reaction has a standard potential of minus 1.23 volt, meaning that ideally require a potential difference of 1.23 volt to split water. This is the potential difference, 1.23 volt. So in a non-spontaneous reaction, the E0 net is always less than 0. This is the electroplating concept where different materials gets plated. Like these are the golden color, brass color, silver color. So this is done through the process or mechanism of the electroplating, where where uh, mm, the metal which color you wish to put on your material is your anode. That means here Ag or silver is gets oxidized to give Ag plus plus release of electron. So by release of electron, what happen? This solution which is silver nitrate, this should be dipped in the same ion solution, that is silver is dipped in silver nitrate. So this the negative ion and this Ag plus ion in the solution gets deposited on this spoon, and this spoon becomes your silver color. This is a mechanism of electroplating, and this mechanism is very much, or this process is very much popular in different jewelry processes or industrial processes when there is manufacturing of your some imitations nut bolts like um, JS German silver. These are the things where electroplating is generally used. In electroplating, the anode is made up of the metal. You want to use the coat the surface, as I already know, anode is the silver, and the salt solution, the silver is dipped in silver nitrate, and it gets oxidized to release electron, and the positive ion gets into the electrolytic solution, and these positive ions are then reduced on the surface of the cathode, and how this electroplating is supposed to be happen. So these are the parameters, quantitative part of electrochemistry. That is, first one is the current. It is the rate of flow of electricity or electric charges. Yes, it is the rate of flow of electric charges. It is known as the current. The SI unit of current is ampere, and I equal to Q by T. This is the formula, or Q equal to IT. Q is the total electricity. Q, that is in coulomb. I is in ampere, that is current, and T is in second, that is time. Then Q equal to IT. Then we have some relation between your free energy, that is in thermochemistry, thermodynamics. With electrochemistry, the relation is del G, that is change in free energy, equal to minus NFE, where N is the number of electron transfer, F is the Faraday, and E is the electromotive force or a potential difference, EMF or potential difference. And just remember, in thermochemistry or thermodynamics, it is very much clear that when free energy change is negative, the reaction is spontaneous, and when it is positive, the reaction is non-spontaneous. So the del G becomes negative when E is negative, because between N, F, and E, E is the variable, N is constant, and F is also constant. So only variable is E. So when E is negative, the del G value negative, and the reaction becomes spontaneous. When E is positive, the the value at the right hand side becomes becomes if it is negative, the value becomes positive, and the reaction becomes non-spontaneous. There is vice versa. Okay. So this is the reaction. Sorry, this is the relations between your free energy with your equilibrium constant, and this is free energy with electrode potential. This is del G equal to minus RT ln K, del G equal to minus NFE. These are the two equations you should remember for different problems, for solution of different problems. And we have from this equation E equal to del G by NF in minus. So this is the real equation, and these are the three parameters which are interlinked or interdependence. That is E0 cell to K, that means it is E equal to RT by NF ln K, and if it is del G and K, it will be del G equal to minus RT ln K. If it is del G and NF E0, it will be del G equal to minus NFA. So how to get this equation? By correlating minus NF E0 cell equal to minus RT ln K. Then E0 cell will be minus minus cancel. We will have RT by NF ln K. So these are some things that when the del G is negative, that when reaction is spontaneous, it favors the product, and E0 is negative, positive, equilibrium constant is greater than 1. When it is 0, that means equilibrium is reached. Neither product nor reactant gets produced, and they are equally favored. When it is positive, del G positive means the reaction is shifted towards reactant side, and the reaction is non-spontaneous. So these are the things in this PowerPoint presentation. Then we have our this one, unit 1, that is basic concept. This is ampere, ohm. Ohm is a unit of your resistance. That is the potential or the force offered by the all the ions to which hinder the flow of electricity. That is ohm. That is the resistance, and it is this unit is given to resistance with the honor of the great physicist, German physicist G.S. Ohm, and similarly, Ampere is given to the honor of French physicist and chemist A.M. Ampere, and they are the pioneers in these fields. Okay, and then a volt, that is Ca volt, is the cell potential. It may be electrode potential or cell potential, standard reduction potential, standard oxidation potential. It is a difference in potential, that is this is otherwise known as EMF, that is electromotive force. This electromotive force has the unit of your volt. Then it is coulomb, that is the total electricity, and it is honored of a French physicist C.A. Coulomb. And the last one is Faraday, that is Michael Faraday, and he formulated that 1 Farad of electricity is equal to 96494 coulomb, or ETA for easy workout of problems. This figure is taken as 96500. It is not 494, it is 96500 for coulomb for easy workout of problems. Then Siemens is the unit of SI unit of your electric conductance. What is conductance? It is the property of an electrode which allows the current or which allows the electricity pass through it. It is known as the conductance. So it is ampere by volt. These are what are the basic laws? There is Ohm's law, I equal to E by R, where I is the current, E is the electricity, R is the your resistance. Okay. Then Faraday's, we have two laws of Faraday, that is Faraday's first law and second law, which was given by the great Michael Faraday. And here the first law said state that uh, the amount of substance deposited or liberated in respective electrodes in an electrochemical cell is directly proportional to the quantity of electricity passed through it. That means it is the quantity of electricity is dependent or is directly proportional to amount of substance produced or liberated at their respective electrodes. This is your Faraday's law. What is Faraday's second law? The Faraday's second law is your when two or more electrochemical cells are connected in series, the amount of substance deposited or liberated is directly proportional to their equivalent masses. So this is Faraday's second law. You just remember here, that is Q proportional to number of equivalents, that is equivalent mass. This is second law. And so Q equal to this is the constant, F is the Faraday, is a constant, into number of equivalent. Equivalent means moles per number of electron transfer n. So this becomes your Faraday's law. Then electrode potential we already discussed. Then we have liquid junction potential. This is known as liquid junction potential. That when the anodic half cell and this cathodic half cell is contacted, or is yes, it is known as a zone of contact, where the movement of electron or electricity is from higher concentration to lower concentration. So this is zero point 0.1 molar, this is 0.01 molar. So what happened? There will be flow of ions from higher concentration to lower concentration through this zone of contact, and this zone of contact is known as a liquid junction, and the potential difference is known as liquid junction potential. Then electrochemical cell already we have discussed. Galvanic cells, what is anode, what is cathode, and this is the notification of your or notation of your mm, electrochemical cell. Then we have the reactions like this. Then another important part is nonce equation. So in the determination of cell potential, we just sum up the oxidation potential of anode plus reduction potential of cathode. But this formula is applied when the standard condition is maintained, that is the concentration is 1 molar. When the concentration changes from 1 molar to other concentrations, like let us it be 0.8 molar, or it be 2 molar or 5 molar or 10 molar. At that condition, the standard state is not maintained. So for non-standard state, the Nernst equation is used, which is formulated in 1889. And the equation is, this is the equation, just see here. Yes, this one. This is E equal to E0, that is E is the cell potential at non-standard condition, or at any condition except standard state. It is equal to E0 cell, that means it is the standard, plus 0.0591 by n log mn plus, this is the reduced state. So this is the formula. You have to remember this formula, that is E equal to E0 cell plus 0.0591 by n log product by reactant. Sorry, if it is plus, it is reactant by product. If it is minus, then it will be product by reactant. Product by reactant means in a reaction, this is the reaction, that is AA gives rise to PP plus RR. So what will be the Nernst equation? It will be E equal to E0. If it is plus 0.0591 by n log a to the power a, b to the power b, divided by capital B to the power small p, capital R to the power small r. Just see here, it is written. And if it gets minus, what happen? If it is minus, then E equal to E0 minus 0.0591 by n log these two, numerator and denominator, gets reversed. That is p to the power p, r to the power r, divided by a to the power a into b to the power b. So you may use the positive notation or negative notation. If you use the positive, then reactant by product. If it is negative, product by reactant. Okay, this is the Nernst equation. And always remember, the concentration at solid state or pure state, it is always taken as 1 molar, and the concentration of electrolyte, it can change from 1 molar to other molars. For example, okay, so now these are the things you just see this one. Here what happened? Here what happened? Yes, this one. The E cell equal to E0 cell plus 0.0591 by 2, because 2 is the number of electron transfer or changed. It is small n, 0.0591 by n. For copper and zinc electrode, the n is 2. It is 2 log copper 2 plus by zinc 2 plus, because copper is at the right hand side, that is sorry, copper is at the, this is the reactant, and the zinc is the product. So that's why reactant by product. So you may use the positive notation for reactant by product, or negative notation for product by reactant. It is depends on you how to use this formula, and used accordingly. Do not confuse. And here no zinc solid or copper solid is written, because the electrode in elemental form or solid state, the concentration is taken as 1 molar. So that's why it is not written here. Only the ions are written here, because these ions are present in electrolytic solution, and the electrolytic solutions have the change in concentration from 1 molar to other concentration. So that's why, the if it is positive, then copper by zinc ion. If it is negative, zinc by copper ion. Okay. Then the cell potential already discussed, that is E right minus E left. Just see. Yes, this one. The electrode potential becomes yes, this one. This is 1.1 volt here. 1.11 volt. We have already calculated, that is 0.34 plus 0.76, it becomes 1.1. So the same thing happen here, 1.1 volt. Then classification of different methods. That a potentiometry means it is the difference in potential, that is the unit is volt. We can use the Nernst equation at different concentrations. Then we have direct potentiometer. Okay, that means in direct potentiometer, we measure a potential difference between electrode immersed in a solution, connecting the cells so formed to a voltage measurement device, that is voltmeter or potentiometer. And the second one is your potentiometric titration is also there, where the acid base titration is governed to a definite concentration of base or alkali. Um, Now the acids are added through burette, and gradually for every drop of addition, the change in potential will be noted, and a graph will be plotted between the volume added versus the potential, and we will have the maximum concentration of maximum addition of the volume, that is the titrant, which is responsible to have the maximum potential. This will be the potentiometry graph. Then in our voltmeter very easy. It is a voltmeter means it is just use of a voltmeter, that is to anodic half cell with cathodic half cell. We just connect one voltmeter, and the voltmeter will show the EMF. Then the polarography, it is another method which is developed by Prague, Czechoslovakia in 1920. So it is a dropping mercury electrode. We will discuss in details in our next classes what is a DME and how polarographic measurements are happen. Okay, so this is just dropping saturated calomel electrode and the measurement of your potential difference. Then we have, and the next part will just and another one important reaction equation is there, that is Ilkovic equation. This is Ilkovic equation given by D. Ilkovic, and the equation is ID equal to 708 Nm 2 by 3 D half T 1 by 6 C, where ID is the diffuse current or diffusion current, N is the number of electron transfer, and M is the rate of flow of mercury, and this is related to our polarography. Okay, we will discuss it in detail in our next classes. And D is the diffusion coefficient, and T is the time, C is the concentration. So from this equation, diffusion current direct proportional to concentration, which is equal to ID equal to Kc. Okay. So and then another that is related to a current, that is amperometry, and we have the last thing, we will have electrogravimetry or coulometry. That is gravimetrically, that is gravimetry means it is determination of determination of elements or compounds in by weight. It is known as gravimetry. So here the weight measurement is done by the application of electricity, so that is known as electrogravimetry. So generally copper, nickel, these are gravimetrically estimated, or this is by weight estimation by electrogravimetric apparatus. Then coulometry is there, where current is used, that is coulomb. So from coulomb it is coulometry. So how much Faraday, that is 1 Faraday equal to 96494 coulomb or 96500 coulomb. So from that relation we will determine the amount of current passed through it. So these are the equations related to our coulometry. That is this is the number of electron transfer. It is equal to total electricity passed divided by NF, means it is number of electron into F is the Faraday. Then we have potentiostatic. Potentiostatic means here the potentiostatic coulometry total electricity with the time. Then amperostatic coulometry, where current becomes static. And this is constant current coulometry also. And the formula is used, that is IT equal to Q or Q equal to IT. And the last part will be conductometry. In conductometry, we have migration in terms of conductometric method. Under this condition, the resistance of the cell depend upon the velocity of the ion. This depend of the conductance, that is your reverse of resistance, that is ohm becomes ohm inverse, or this is Siemens unit. So here the flow of electron is measured, that is our conductometry. Then classification, just see this table, this hierarchy, and this is a electroanalytical method, which is of mainly of two types. Interfacial means surface method, or bulk method means it is depth method. Okay, bulk method. So again, the interfacial method is of two types, that is if static methods are here and dynamic methods are here. If and the bulk method is of two types: conductometric, that is G equal to I bar, and the G is the conductance equal to inverse of resistance 1 by R, and we have conductometric titration, that is by volume. Then interfacial is of two types: static method and dynamic. Static method means potential or current becomes static. Then we have potentiometry and potentiometry titration. Potentiometry means it is volumetric analysis. Potentiometry means it is potentiometry means it is the difference in potential in terms of volt. Then dynamic, it is control potential or constant current. We have two parameters, that is potential and current. If potential is controlled and current is constant, then we have control potential. We have four types, that is constant electrode potential coulometry, voltammetry, amperometry titration, and electrogravimetry. This is under control potential. We have the control switch is with us, that we have we may decrease or increase the potential or the current or the electricity pass through it. Then we have constant current. Under this, we have two types, that is coulometric titration and electrogravimetric by mass. So these are the different types of electroanalytical methods. We will discuss these things in our later classes. Okay, so let's have the second unit, that is related to your, that is just related to your potentiometry. I have one. I have one potentiometric. Yes, potentiometric method here. So in potentiometric method, so before going to this is a very easy part of your electroanalytical method. That is, uh, we have to add in potentiometry titration. What happened? We have to add the volume of the titrant and followed by measurement or note down our the potential difference through voltmeter. This is potentiometry titration. So up to this, is there any doubt or something related to the basic part of electrochemistry, or anything else you may wish to ask, or else we may go to chapter unit 2. Is there anything else you may, other students, any of you want to ask? Okay, so if no questions are there, then let's have a 5-minute break here, and we will exactly meet at 7 p.m. exactly at 7 p.m., and we will have our next unit, that is potentiometry. So till 7 p.m. Uh, so let's have some refreshment and um, drinks. Okay, thank you. Thank you, students. So let's have our second unit discussion, that is related to your potentiometry, and I think this is over. Yes, this is potentiometry. Is it visible, students, on the
Yes, sir.
oh, okay, thank you. So in the potentiometric methods, we have the indicator or reference electrodes are there, which are used to have the difference in potential, and also we will have the second type of potentiometric method, which involve your potentiometric titration also there. So two types of things are here. There is potentiometric method based on measurement of the potential of electrochemical cell in absence of appreciable current, and the basic parts are reference electrode, which we will discuss one by one. Then what are the indicator electrodes are used, then salt bridge, then what are the devices which we use for the potential measurement. So this is the a reference electrode is symbolized as ERF, that is a reference electrode potential. This is a salt bridge, which is equivalent to your liquid junction potential or liquid junction, that is EJ. It is the contact zone of contact, that is liquid junction potential, and the last one will be the indicator electrode. So E cell will be E indicator minus E reference plus EJ, that is indicator electrode potential minus reference electrode potential plus liquid junction potential. So this will be the net E cell of this cell. And here it this reference electrode, it is generally calomel electrode, that is made up of mercury and mercury chloride, mercury in mercury chloride solution, that is otherwise known as calomel electrode. And one metallic electrode is used here, that is metallic electrode, indicator electrode, which is also has a salt bridge, that is just same as your liquid junction potential. So these things are there, and which is directly connected to the potentiometer. One device is there, instrument, which is known as potentiometer, and that potentiometer will show the difference in potential in millivolt MV. Then we have, what are the reference electrodes used, that is, as I know, as I said you, that calomel electrode, we have silver chloride electrode. These are the types of electrode which are frequently used or popularly used as your reference electrode. So need one electrode of the system to act as a reference against the potential measurement can be made, or which is based on the relative comparison. That is the the elect potential of the indicator electrode, which we are trying to estimate or determine in comparison to the reference electrode, when in comparison to an electrode which is the reference electrode. What are the desired characteristics of reference electrode? It should have a fixed potential. This is very important. Like a standard hydrogen electrode. Standard hydrogen electrode has the potential of 0 volt, which is fixed. Whether it is coupled with a higher reduction potential element or lower reduction potential element, it is neither affect the potential of the standard hydrogen electrode, that is 0 volt. If it is coupled with zinc, it gives potential of 0 volt. If it is coupled with copper, it also gives potential difference of 0, sorry, potential of 0. So that means the potential should be fixed. It should be constant response to either electrode, then insensitive to the solution or electrolyte where it is dipped, and it also should obey Nernst equation in different concentrations. It should be reversible, rugged and easily assembled, always treated as left hand electrode. So standard reference electrode is always the anodic part of the cell, and the common will be calomel electrode, that is mercury in mercurous chloride and KCl, and silver in silver chloride. And this is the first one, standard calomel electrode, SCE, or this is the calomel electrode. The reactions are the cell representation. It is the half cell representation because it is the half cell of the total cell, that is a reference electrode. These are the dimension of which you need not require to remember these things. Okay, just representation is silver dipped in silver, mercury dipped in mercurous chloride saturated with potassium chloride with some molar concentration. Then what is the cell reaction? Here silver chloride is changed to silver metal and release of 2 chloride ion. Okay, that means what happened here? Now here silver is in +1 oxidation state. Here silver is 0. That means +1 to 0 means it gets reduced. This is silver is in +1. Here silver is 0. That means +1 to 0 means it gets reduced. Simultaneously, this is the reduction half cell, or it depends to which it is coupled. It is widely used. Equilibration due to temperature change is slow. Leakage of KCl into the sample. Mercury contamination should be avoided. Less common than once they were used. Still preferred for some certain applications. So this is the disadvantage of this reference electrode, that leakage of potassium chloride sample from this. Just see this one. This is the mercury electrode or calomel electrode, where a saturated KCl solution is here. This is the KCl crystal. The calomel paste means this is the mercury. Okay, so this is the mercury, and this is the electrode which is coupled with our indicator electrode. So these are the temperature 0.1 molar KCl, calomel 0.3 molar KCl. These are the change in concentration, and these are the temperature with the change in potential. Here M and saturated refers to the concentration of KCl and not mercurous chloride. So this is M and C. M stands for your KCl concentration, and this is the second type, the silver chloride electrode, where silver is placed in silver chloride solution, and silver chloride is precipitated. Okay, so here silver, this is a representation, silver in silver chloride saturated, and we also have potassium chloride in specific concentration. What is the silver reaction? Silver chloride gets converted to silver solid and chloride ion, and this is the mechanism or instrumentation of your silver chloride electrode, where this is the silver wire is here, and this is KCl saturated with silver chloride. This is saturated solution, and these are the different dimensions. But the advantage, one advantage is that silver chloride electrode cannot be used, can be used above 60 degrees centigrade, and but calomel electrode will not use due to because mercury is a liquid at mercury is a metal, but in liquid state. So that's why that if there is temperature variation, there will be difference in level, which may affect the potential difference measurement. What are the disadvantages? Silver react with more ions, plugging of the junction between electrode and electrolyte. So this is silver is generally reacts with the ions present, which may hinder the junction part of this electrode. And these are the precautions. I must, these are the same thing, that is different concentration. What are the voltage with SHE, standard hydrogen electrode? Okay. Then indicator electrodes, uh, detects or respond to the presence of analyte. Ideal indicator electrode respond rapidly and reproducibly to change in the concentration of an analyte ion. Three common type: metallic indicator electrode, membrane electrode, and ion selective. So in metallic we have electrode of first kind, second kind, third kind, and the redox indicator. And in membrane we have crystalline and non-crystalline. In ion selective electrode we have field effect transistors are there, which are used for your ion selectivity. Indicate the first type, that is metal electrode in first kind. So this involves single reaction, that is uh, Xn plus accept electron to gives X solid. That means here copper, for example, copper 2 plus gets electron to give copper solid, and here are the electrode potential of indicator electrode equal to E0 copper minus 0.0591 by 2 log concentration of copper solid, that is product by reactant, because this is minus means this will be product by reactant. Product means this is copper solid divided by copper 2 plus. As I already said, the element in solid state or elemental state, it is taken as 1 molar. So copper solid, the value is replaced here 1. So this will be 1 by activity of your copper 2 plus. This will be the um, this will be the partial pressure of copper. Then we have metallic, these are the problems. Just go, I will share this at the end of this paper. Just go through these things, this is not very much important. And the second type, then we have second type, that respond to activity of anion that forms sparingly soluble precipitate. Sparingly soluble precipitate means the best example is silver chloride. So this is silver chloride gain electron to give silver solid and chloride, and here E0 is 0.222 volt. So here indicator electrolyte, so indicator electrode potential is this one. So we have the net will be this one. Then the this is the second type example, that is mercury electrode, that calomel electrode, that is, this is an example detection of EDTA ion, that is Y4 minus with mercury electrode. EDTA is ethylene diamine tetraacetate ion, which is hexadentate ligand, and it always 4 minus charge is there because tetraacetate ions are here, and that's why it is symbolized as Y4 minus. And these are the reactions, and these are the electrode potentials calculations. Okay. And then the third type, the third type related to the metal electrode respond to different cation linked to cation by intermediate reaction. So two things are there, the different cation are here, and these are linked to intermediate reactions. Then we have the same thing, that is EDTA by mercury electrode, the second kind. That means the same metal electrode respond to different cation, and the linked cation by an intermediate reaction. This is the third type. That the intermediate reaction will be there. For example, this is calcium Y2 minus will give, this is calcium EDTA, will give calcium and EDTA. This is the formation constant. And if I go for the electrode potential, this is formation constant K minus this one log this one. Then the final will be your K dash equal to K minus 0.0591 log of the mercury electrode has become an electrode of the third kind for calcium ion. This is the third kind. Then indicator electrode of type 4, that is metal redox indicator. Redox indicator means where reduction and oxidation take place simultaneously. These are generally the inert raw metals, say platinum, gold, or palladium. Like in standard hydrogen electrode, platinum is generally used for as indicator electrode, and here cerium gain electron in platinum electrode to give cerium 3 plus, and this is the electrode potential equation. Then membrane means just a separator will be there. The concept of adsorption will be here. The adsorption means it is the settlement, or it is the settlement of foreign ions on the surface of a material, and that surface is known as adsorbent, and the foreign materials are known as adsorbate. So adsorbate ions or molecules gets adsorbed on the surface of adsorbate. So this is often called ion selective electrode or Plon electrode, and these are the function of pH, P function, that is pH, PCA or P nitrate. This is depends on nature of membrane, the metallic electrode, oxidation reduction reaction, and we have liquid junction also plays an important role, as this is the membrane. So this acts as the zone of contact or liquid junction. These are desired properties: minimal solubility, need for electrical conductivity, selective this is reactivity with analyte. This is membrane electrode, that is pH electrode. This depends on the pH meter is there. That is two reference electrodes are here. One is standard calomel electrode or one silver chloride electrode, and pH sensing. Just pH meter is introduced here, and this is one of your indicator electrolyte. Then this is the pH determined by formation of boundary potential across glass membrane. This is not in your syllabus. This is glass membrane, sir. Then this is the cell potential, the same thing, that is oxidation potential of anode plus oxidation reduction potential of cathode. These things are not in your syllabus. Let's skip this one and go to our PDF. Yes, this is a measurement of potential to potentiometer or voltameter. Okay, then we have this is the calomel electrode, or this is your cadmium mercury electrode, where mercury and cadmium both are here, and mercury is dipped in mercury sulfate and cadmium is cadmium sulfate, and there will be a salt bridge here also. So direct potentiometry, this is the Nernst equation is obeyed. Okay, so Nernst equation is obeyed here, and this is direct potentiometry. Reference electrode already discussed. This is standard hydrogen electrode, where platinum is here and hydrogen gas is bubbled. Hydrogen HCS, sorry, acid solution is taken as H plus, and this H plus is converted to hydrogen gas. Then we have calomel electrode already discussed. This is the calomel electrode. Then we have silver chloride electrode. This one. Then indicator electrolyte or electrode already. This is also discussed. Then we have mercury electrode, that is uh, one of your indicator electrode, that is mercury 2 EDTA complex, ethylene diamine tetraacetate complex. These are the equations. Then membrane ion selective electrode. Then we have determination equilibrium constant. The reaction here, the equation is this one. In our first PowerPoint presentation, I have already told you that del G equal to minus NFE and del G equal to minus nRT ln K. So if it is ln becomes log, there will be multiplication of 2.303 factor. So this will be minus 2.303 RT log K. So the relation will be log K equal to NFE0 say by 2.303 into RT. Then we have second type, potentiometric titration. Number one is potentiometry, that is an instrument. and this is a potentiometric titration. That is acid base titration will be there like this. Just wait. Acid base titration will be just wait. Hello.
Yes, sir.
Yeah. So we have the next part, that is the potentiometric titration. That is here the reference electrode is the calomel electrode is used, and we have one burette which we use for addition of the titrant. That is that if it is acid base, then it is acid solution, and we took here the alkali or base, and this is the ion meter with millivolt scale. This is just voltameter type which indicate the potential difference. So we will add drop by drop, and we will note down the potential difference. So we will have this type of plots, that this is a volume of titrant added with the change in volt, that is a potential. So if the plot is like this is the equivalence point, where there will be saturation will be here, there will be no potential change. Okay, that means after addition of the titrant, the potential change will be steeper. So this will be the equivalent point, equivalence point or end point. And if I take the first derivative of these readings, then we will have this type of plot. And if I take the second derivative, then this type of plot will be there, and this will be the equivalence or end point of this reaction. Then types of potentiometer titration, we have a neutralization, means a seed based titration here, where we will use the Henderson equation, that is concentration of Ha, A minus Ha, then by change in pH, how the dissociation constant or pK value will change. Then we have oxidation reduction reaction, means redox titration we will have also. Then precipitation titration means precipitate will form, that is silver converted to silver chloride or silver iodide. These things also can be measured. Then complexometric titration with ADTA. Then we have differential titration also, and automatic titration also. So these are the things you have to read carefully. And there is a figure here, that is mercury electrode, the calomel electrode is here. And these are very much simple things. You have to just remember the one equation, that is Nernst equation. This is applicable to every electroanalytical method, this Nernst equation, because this Nernst equation is for non-standard situation, where the standard condition is not maintained. What is standard condition? The standard condition is 1 molar concentration, but always 1 molar concentration will not be there. So we have to use this Nernst equation, that is E equal to E0 plus 0.0591 by n log reactant by product. If it is minus, then it will be product by reactant. Just remember this only thing, then you will able to solve different problems, or able to write the derivations, definitions very easily. Just see this one, this is oxidized form, gain electron to give reduced form. So what will be the equation? If it is positive, that means oxidized form is above and reduced form is at the denominator. And if it is minus, it will be reduced form by oxidized form, this much. So today we completed unit 1 and unit 2 of your MCH 2 paper, sorry, 4 paper. And if anyone has any doubt related to today's discussion, or anything else related to your program, practical, anything, you may ask or share. um, we have only 5 minutes left. I think today's class is very much understandable, because these things are in your plus at plus two level. and in your at your BSc level, these things are very much common in chemistry and physics also, and mm, and in your PGDSC course, uh, and your IGNO material is very very good. If you go through it in details, you will get many informations. And actually, due to paucity of time, lack of time, we are unable to cover all the things bit by bit or line by line. But I just try to put the basic things which are involved in different electroanalytical methods and your potentiometric application, and hope you will got get hope you will go will get some information or idea or knowledge on this part of chemistry. Is there any questions or queries or anything else you want to ask or share? You may. So over to you, students. Okay. So Dr. Mona Lisa Mahapatra has taken, I think, she took MCH-3 paper, I think, and Dr. Rajesh took first paper MCH-1, that is the spectroscopic part, and I have taken the second paper, that is the separation method. And today we will have the first part of your electroanalytical method. So if no questions are there, today's class is wind up here, and we will have unit 3, and then we will move to next level. So I hope you all will uh, remain safe, and uh, my best wishes. Okay, so thank you to all.
Thank you, sir.